All right, today we are diving deep into the atom, the fundamental building block of literally everything. From the stars in the sky to the very biology that makes us who we are, understanding the atom is absolutely essential. It's the foundation of modern physics and chemistry. You know, for thousands of years, this was a question for philosophers. The ancient Greeks even came up with the idea of atomos, this tiny, uncuttable particle. But it's really only in the last couple of centuries that science started to peel back the layers and uncover the elegant and, frankly, deeply weird reality of what an atom actually is. Okay, so to make sure we're all on the same page, let's start with the modern definition. An atom has the super dense, positively charged center called the nucleus. That's where almost all its mass is. And surrounding that is this fuzzy cloud of negatively charged electrons. The way these parts interact with each other, well, that's what governs pretty much all of chemistry and a huge chunk of physics. So here's our game plan for this explainer. First, we'll break down the atom's basic parts. Then, we'll take a journey through the history of its discovery, dive into the bizarre quantum model, see how atoms get their identity, how they build our world, and finally, we'll look at their role in our modern lives. Let's start by looking at what an atom is actually made of. Turns out there are three main subatomic particles that really define its structure and what it can do. So, packed into that tiny nucleus, you've got protons, which have a positive charge, and neutrons, which have no charge at all. They're neutral. They're both pretty hefty particles and have almost the same mass. Now, orbiting way out from that nucleus is the electron, and this thing is incredibly lightweight, almost 2,000 times less massive than a proton, and it has a negative charge. It's that classic attraction between the positive protons and the negative electrons that holds the whole atom together. The scale here is it's almost impossible to wrap your head around. The radius of the whole atom, from the center of the nucleus all the way out to the edge of that electron cloud, is about 100,000 times larger than the radius of the nucleus itself. That means an atom is almost entirely empty space. To put it another way, if an atom were the size of a giant sports stadium, the nucleus would be a single marble sitting right in the middle. But you know, we didn't just figure all this out overnight. This picture of the atom is the result of a long, long scientific journey, where each new model was built to explain some new experiment that the old model just couldn't handle. So our journey starts way back in the early 1800s with Dalton and his idea of simple solid spheres. But then things really kick into high gear around the turn of the 20th century with Thomson, Rutherford, and Bohr. Each one of them added a crucial piece to this giant puzzle. John Dalton was a chemist, and he was looking at how elements combine. He noticed they always did so in simple whole number ratios. For example, he saw that in two different tin oxides, for the same amount of tin, the amount of oxygen was in a simple 1:2 ratio. This made him think that matter had to be made of these discrete little units, atoms, which he pictured as tiny solid balls. Then, in 1897, J.J. Thomson discovered the electron. This was a huge deal. The uncuttable atom actually had smaller parts inside it. So, to make sense of this, he proposed what we now call the Plum pudding model. He imagined the atom was this sort of diffuse ball of positive charge, with these little negative electrons scattered throughout it, kind of like plums in a pudding. And this is where the story gets really good. To test this plum pudding idea, Ernest Rutherford set up a now famous experiment. He fired these positively charged things called alpha particles at a super thin sheet of gold foil. He expected them to just fly straight through. But what he saw was stunning. Most did go through, but some were deflected at wild angles, and a few even bounced straight back. He later said it was as incredible as if you fired a 15-inch shell at a piece of tissue paper, and it came back and hit you. The only way to explain this shocking result was if all the atom's positive charge and almost all of its mass were crammed into an impossibly small, dense center, what he called the nucleus. So he proposed the electrons must be orbiting this nucleus, kind of like planets orbiting the sun. The atom wasn't a pudding anymore. It was a miniature solar system. But there was a big problem with Rutherford's model. According to the physics of the time, an orbiting electron should be constantly losing energy, which would cause it to spiral into the nucleus in a fraction of a second. Matter shouldn't be stable. So Niels Bohr came along and proposed a radical idea. What if electrons could only exist in specific, stable energy levels, or orbits? They could jump between these levels, but they couldn't exist in the space in between. Now, Bohr's model was a huge step forward,
But it was also the last time we could really use our everyday intuition to think about the atom. Because what came next? Well, it required a complete break from classical physics and takes us into the truly strange quantum world. In 1926, Erwin Schrödinger came up with a set of equations that changed everything. He described electrons not as little balls zipping around in circles, but as waves. His math gives us these things called orbitals, which are three-dimensional regions of space where you have a certain probability of finding an electron. So the idea of a neat, predictable path is gone. It's replaced by a fuzzy cloud of probability. And this probabilistic nature is locked in by Werner Heisenberg's famous uncertainty principle. It basically says that the more precisely you know where an electron is, the less precisely you can know where it's going, and vice versa. And this isn't because our measuring tools aren't good enough. It's a fundamental, built-in feature of how the quantum world works.
Okay, so now that we have this bizarre, fuzzy quantum picture in our heads, let's get back to something a little more concrete. How do we actually tell one type of atom from another? Well, it all comes down to what's going on in the nucleus. An element's entire identity comes down to one thing: its atomic number. And that's just the number of protons in its nucleus. It's like the atom's unique ID number. Every single atom in the universe with 6 protons is a carbon atom. Every atom with 79 protons is gold, no exceptions. If you change the number of protons, you have a completely different element. Now, the mass number is just what you get when you add up the protons and the neutrons. And while the number of protons defines the element, the number of neutrons can actually change. We call these variations isotopes. Take hydrogen, for example. All hydrogen atoms have 1 proton, but the most common kind, hydrogen 1, has 0 neutrons. Deuterium has 1 neutron, and tritium has 2. They're all still hydrogen, they just have a different mass. So we know what atoms are, and we know how to identify them, but how do they actually do anything? How do they come together to build the entire world around us? Well, it all comes down to how their electrons are arranged. The key players here are the valence electrons. Those are the ones in the atom's outermost shell. See, atoms have this powerful drive to be stable, which usually means having a full outer shell of electrons. To do this, they interact with other atoms. Sometimes they'll transfer electrons, creating ionic bonds. Other times they'll share electrons, creating covalent bonds. And these bonds are the glue that holds atoms together to form molecules, everything from a simple water molecule to incredibly complex DNA. You know, this deep understanding of the atom isn't just an academic exercise. It has unlocked technologies that have completely defined our modern world, and it's also given us this profound connection to the universe itself. Think about it. We harness the energy locked inside the nucleus for nuclear power. We use the properties of nuclei in MRIs to see inside the human body. We even use the predictable decay of isotopes to figure out how old ancient fossils are. But maybe the most amazing part is this. Every carbon, oxygen, and iron atom in your body was forged in the heart of a star that died billions of years ago. We are, quite literally, made of stardust. So we've gone from thinking about the atom as this simple, indivisible ball to understanding it as a probabilistic quantum wave function. Every single step on that journey has revealed a deeper, more complex, and more powerful reality, and the exploration is far from over. Which leaves us with a fascinating question. As we keep probing deeper and deeper into this subatomic world, what new picture of reality is still waiting to be discovered?